Section 3.7 is about optimization. What's optimization? Making something as absolutely big as you can. In this case, we wanted, and what we did just a minute ago, we wanted to make the biggest possible box. So optimization can be finding the absolute maximum, or optimization can mean finding the absolute minimum. When would you want to find the absolute minimum on something? Okay. Or when you're building something, you might want to build it using the minimum amount of material, which in theory should minimize your costs. That sort of thing. So optimizations for us will mean finding absolute maximums, finding absolute minimums. Okay, here was the situation we just had. We started with a piece of paper, which was 11 by 8.5. And what we did is we cut a corner out of each side, and we folded it up, and we made a box with no top. And these squares were all the same, x by x. The real question is, how much should we cut out? How much should we cut out in order for the box to be as big as possible, to have the maximum volume? How would you find the volume of this box? Volume is length times width times height.
So it would be minus 2x from the width and height.
Correct. I started, I guess we'll call this one length. It started 11 inches, but I cut x off of this end, and I cut x off of that end. So how long is that now?
About L minus 2x times W minus 2x times x.
Well, it would actually be 11 minus 2x, wouldn't it be? We know it started as 11. So that would be 11 minus 2x would be our length. Our width is the same thing. We started 8.5 inches wide, but we cut x off of each end. And then our height, once you fold it up, the height is going to be x. So there's our formula for volume. Now, what do we want to find? We want to find the optimal value for x. We want to maximize the volume. How do you find the maximum or minimum of something? You find the derivative. And then what do you do with the derivative? Set it equal to 0 or undefined, and that gives you your critical points. Actually, critical numbers, but we'll find the critical points. And once you have the critical numbers, how do you determine if your critical number gives you a minimum or a maximum? You can use the first derivative test, or you can use the second derivative test. We had two derivative tests, didn't we? All right, so I'm going to go ahead and I'm going to take the derivative of this thing. So I'm going to call this v of x. So v prime of x is, how do I take the derivative of that thing? Product rule. All right, so I take the derivative of the first one. What's the derivative of the first one? Negative 2. And I leave the second one alone, 8.5x, 8.5 minus 2x. And I leave the third one alone. Plus, then I switch it. I take the derivative of the middle one. What's the derivative of the middle one? Negative 2. And I leave the first one alone, 11 minus 2x. And I leave the last one alone, that's x. Plus, one more to go. I leave the first one alone, 11 minus 2x. I leave the second one alone, 8.5 minus 2x. And I take the derivative of the first one. But the derivative of the first one is 1. Oh, I'm sorry, the derivative of the third one. The derivative of the third one is 1. All right, now what I need to do is I need to take that derivative and I need to set it equal to 0 and I need to solve that equation. So I think what I will do, I think I'll take this negative 2 and distribute it through, take this negative 2, distribute it through, FOIL over here, combine all my like terms and see what I have. A whole bunch of algebra to do now. What's negative 2 times 8.5? Negative 17 plus 4x. And then all those got to be multiplied by x, don't they? So let's write that as negative 17x plus 4x squared. So distribute the negative 2 through and distribute the x through. Same thing on the next one. That's going to give me negative 22x plus 4x squared plus, oh, I might need a calculator here. Let's see, got 11.5, or 11 times 8.5. 93.5 minus 22x minus 17x plus 4x squared. So it looks like I have 12x squared minus 17x minus 22x minus 22x minus 17x minus 78x plus 93.5. And I need to set that equal to 0 and I need to solve it. Quadratic formula. All right, program. Quadratic formula. 12. Negative 78. 93.5. Calculator tells me x should be 78 plus or minus the square root of 159 divided by 24. So x is approximately, we get two answers, 4.915, or x is 1.585. One of those answers is acceptable. One of them is not. X cannot be 4.9. Why not? Because if I cut 4.9 off of this end and I cut 4.9 off of this end, I just cut off 9.6. I only got 8.5 to start with, don't I? I can't cut off 9.6 if I only have 8.5 to start with. So that one's got to be wrong. So x should be about 1.585. Now there's one more thing to do. Actually, there's two more things to do. Check what? And what do I need to do to check to see if that value really is the right one?
Plug it back into the original.
I should plug it into the original to find the volume, because that was the ultimate goal, was find the maximum volume. But how do I know that that x equals 1.585 is going to give me a maximum? How do I know it's not a minimum? I have to test to make sure it really is the maximum. So I really need to either do the second derivative test or draw a number line. Which one do you want me to do? Number line? All right. That's not the one I wanted to do, but I'll do it anyway. 1.585. What's my favorite number bigger than 1.585? 2. I plug 2 in. Well, that's 12 times 4. 48 minus 78 times 2. Plus 93.5. I get negative 14.5. So, decreasing there. What's my favorite number smaller than 1.585? 0 is my favorite number, but I am not allowed to use it. Why not? That was going to be my question. What's wrong with 0? X cannot be 0. I can't cut off nothing. If I cut off nothing, I don't have a box. So you do need to be careful about domain on these problems. X cannot be 0. We already saw that here x was 4.9. That was too big. On the other hand, x can't be 0. X can't be a negative number. It cannot. So I would really need to pick one. And I'm going to leave it up to you to pick one, plug it in, show that you do get increasing there. Okay? All right, but now here comes the big question. The first derivative test promises me that I have a relative maximum. I didn't want a relative maximum. I wanted the absolute maximum. So how do I know if I have the absolute maximum? Use technology. Okay. 11 minus 2x times 8.5 minus 2x times x. Graph. Well, let's see. I got to change my window here.
Can you just zoom fit it?
Can I just zoom fit it? I didn't know that was a verb, but I guess I can. Zoom fit. Yes, I can zoom fit it. But I do not like zoom fit very much because it usually does not give you a very good window. All right, so I know from computing our volumes that we did when we physically did it, how big did the volumes get? Somewhere around 66 cubic inches. So I think I want to go from like negative 60 to 60. I think I could go bigger than that, negative 70 to 70. All right, so right here is x equals 1.5 something, something, something. So it is a relative maximum. Is it the absolute maximum?
In the domain it is.
Excellent. In the domain it is. What's the domain?
Anything above 0 to below
11. Sorry, 11. Before that.
Well, if it could be as big as 8.5, then what was wrong with 4.9?
It's 4.25.
It's got to be less than 4.25.
It's going to be less than 8.5 divided by 2, right? Which is 4.25. So, between 0 and 4.25, which is our usable domain, is this the absolute maximum? Yes. All right. So, and then our volume would be the volume. If I plug 1.585 in, I would get 66.148. So I made my box 0.148 cubic inches bigger than you did. Those of you who had 1.5 inches. All right, so what we really have in this case is there's a theorem that we're using. If f of x has exactly one critical point in an open interval, and that critical point is a relative max or min, then it is an absolute max or min. So that's how you can tell if you have absolute minimums or maximums. Basically, you have absolute minimums and maximums when you only have one critical point. Why is that? What's special about having only one critical point? How come if we only have one critical point, then that has to be the absolute maximum? Because in order for it to not be the absolute maximum, the graph would have to turn around and go back up higher, wouldn't it? But if the graph turns around and goes back higher, what happens right here? Where the graph turns around, there's a minimum, which means there's a second critical point. So if you only have one critical point, the graph can only turn once. In order for the graph to turn twice, you have to have a second critical point. Is that better? Oh, you can't see the words. I'm sorry. What's the word?
So in 4.915 is that other critical point. There's the other. It's the minimum, right?
Well, it's the minimum for this function. It's the minimum for that function. So if you were to forget for a minute that this function stands for volume, then this one would have a relative minimum at that point. But that really wouldn't make any sense for this case because this would be saying we have a negative volume. We can't have a negative volume. So in a lot of these optimization problems, you do need to be concerned about your domain. In this case, x has to be between 0 and 4.25. Can x be 0? No. Can x be 4.25? No, why not? What happens if x equals 4.25? All you did is cut the piece of paper in half, didn't you? Again, you wouldn't have a box. All right, so let's take a look at some of these other problems. A farmer plans to fence a rectangular pasture bordered on one side by a barn. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. I have a typo? What dimensions would cause the east amount of fencing if no fencing is needed along the barn? So I think the typo is it should be least. Least amount of fencing. Okay, so here's the idea. We have a barn, like so, and we're going to build a fence like this so that our animals can come out of the barn and eat. No? All right. So, what's our goal here?
Figure out what the optimal amount of fencing is to be able to house 180,000 square meters of pasture.
So our goal is least amount of fence. Can't spell fence. So there's the thing we want to minimize or maximize. In this case, by optimizing, we mean find the minimum, use the smallest amount of fence possible. Why do we want to use the smallest amount of fence possible? It has the least cost. The least amount of fence you use, the least cost it causes to build the pen. But we do have a restriction. And the restriction is the area needs to be 180,000 square meters. The pasture must contain 180,000 square meters.
So you're going to end up getting an exact number.
So I'm going to get an exact number. We could build the fence bigger if we wanted to. We could build it so that it's more than 180,000 square meters, but that again would cost us more money because we'd have to buy more fencing. Okay, so what I need is a formula for amount of fence. I need an equation of some sort for amount of fence. So what's my equation for amount of fence?
2 length times 2 width minus 4.
Okay, so I don't remember which one you call. Is this one width or is this one length?
Well, the one that's bordered by the barn is width.
Okay, so you're calling this one width,
Yeah.
and this would be length, and this would be length. Correct? So the amount of fence, I need to build 2 sides of length L
What am I trying to say? So,
and 1 side of length W, correct?
if the area is then it's the perimeter that we're getting the fencing.
Correct. Our fencing is really the perimeter, except it's not truly perimeter in this case because we only need to build 3 sides. So the amount of fencing is almost the perimeter, except we only have to build 3 sides. If the barn wasn't there and we had to build all 4 sides, then our amount of fencing would simply be perimeter.
But 180,000 is 1 length and 1 width.
Correct. All right, so we have a formula for fence, but it's not a formula we can use.
There's going to be 2 formulas.
Correct. What's wrong with this formula? How come I can't use this formula?
2 variables.
It's got 2 variables. When we do derivatives, how many variables can we have? 1. So, this is typically what's going to happen in these problems. You're going to have a formula which is going to contain 2 variables. What you then need to do is use your restriction to get another formula which contains 2 variables, and then you do a substitution.
Yeah.
So what's the formula for our restriction?
L times W equals 180, and then you divide by your L.
Correct. Area is length times width. So length times width is 180,000. We divide by one of them. It truly doesn't matter which one. And then we substitute. I'm going to do W is 180,000 over L. And then we use the technique of substitution. So I'm going to take this, and I'm going to plug it into my F formula. And that gives me what I'm going to call F at L. Is 2L plus 180,000 over L. So I call this F at L because this is now fencing using only the letter L. So function is, my fencing function is now a function of just one variable, just the letter L. Okay, so now I have what I need. Now I have my function. My function only has one letter. Now I know what to do. What do I do? Take the derivative. F prime at L is, what's the derivative of 2L? 2. Plus, what's the derivative of 180,000 over L? Quotient rule. I could use the quotient rule. That's too hard. Think of this as being 180,000 L to the negative 1, and then you don't need quotient rule. You bring the negative 1 down, so that's going to give you negative 180,000 L to the negative 2. Much easier than using the quotient rule. The only time you really need to use the quotient rule is when you have a variable on top and a variable on bottom. If you don't have a variable on top, bring the bottom up, give it a negative exponent, and then just use your power rule. Alright, so I didn't leave enough room on this one, did I? Alright, so now what do we need to do? 2 minus 180,000 over L squared equals 0. So that equal to 0. How do you solve that equation? Negative 180,000 over L squared equals negative 2. Move the 2 over and then cross multiply. Negative 2L squared is a negative 180,000. So L squared is negative 90,000. So positive, right? So L is, I bet it's a nice number like 300. Is that correct? 300? So W would be, I would take this and plug it in back up there. 180,000 divided by 300 is 600? Yes? Yes. So apparently we should build our fence to be 300 by 600. Questions on that? What's that?
It's just asking for the dimensions, not the amount of fence.
What dimensions would be required?
Would it just involve that?
So the dimensions are 300 by 600. Correct? Maybe. Why do I say maybe? We're not done yet, in other words. Gotta check what? We want it to be a minimum. It's possible I just found the maximum. And I did the worst thing I could possibly do. I need to make sure that really is a minimum. I got another question. This derivative is also undefined when L equals 0. So isn't 0 a critical point? What's that? I would have no fence. When I took square roots on both sides, couldn't L also be negative 300? I can't have negative length either, can I? All right, so there really only is one critical point. What I need to do is I need to make sure that that critical point is a minimum. Just to be different, this time I'm going to use the second derivative test. F double prime at L, what would the second derivative be? There's my first derivative. So what's the second derivative? I bring the 2 down. What's negative 18,000 times negative 2? Negative 306, or positive 360,000 L to the negative 3. I plug in 300 reality is I don't know what I get, but I do know when I plug in 300 it's going to be a positive number. How do I know it's a positive number? What's 300 to the negative 3? 1 over 300 cubed, which is a positive number, isn't it? So I would have positive divided by positive. That's going to be positive. The second derivative test sometimes is pretty easy. This is a good example. The other day I told you that I usually only use the second derivative test when I'm using technology. For some of these problems, the second derivative test is really pretty easy. All right, so the second derivative is positive, which tells me do I have a minimum or a maximum? Second derivative being positive means I do have a minimum. So I do believe that's the correct answer. We should build our fence 300 by 600. All right, we'll do the other 3 problems on the sheet on Wednesday.